So I'm glad to present Misha Kornev, who will tell us about nerve realization adjunction and the bar construction.
Thank you. Firstly, I would like to talk about nerve realization context, and let me give the following definition. Nerve realization context is a functor from small category C to some locally small category D. For nerve realization context F, one can consider the left can extension. We can form the following diagram. And can extension along the unit embedding. And it turns out that there is a universal property of the category of press sheaves theorem. Universal property of the category of press sheaves on C. The first point is that universal property of this category amounts to the existence of left adjoint to precomposition that is left can extension. Such that it has invertible unit. And the unit of the adjunction eta. Not eta, but we have a junction, the following junction, and the precomposition with the embedding, and the unit of this adjunction is invertible. Okay. The second point is that the essential image of this functor consists of those functors f from this category to the that preserves all colimits. And the last point is that if D is a category of press sheaves on E, then this essential image is equivalent to the subcategory of left joints. Okay, we can prove this theorem. It's quite simple proof. The first point is equivalent for proving the first point. We should prove that the following statements are equivalent. The first one is for any functor f, any functor f extends uniquely to the functor f bar. The second one up to isomorphism. The second one is that there is an adjunction which is which has an invertible unit. Okay, suppose that there exists f bar, then we can consider the correspondence f maps to f bar. And this is a function. Determined up to isomorphism. Okay, and for any functor g from pre-shifts to d, which forms the following diagram. We have a functor from this category to the category D. This is a G, and this arrow is a composition G with the unit embedding. Okay, and but if we take the left-hand extension of this functor along this functor, then we have a unique natural transformation epsilon, and also we have eta. And this natural transformation epsilon is a co-unit of our adjunction. Okay, and what is the unit of our junction? It's easier to see that it's just a composition. We should take the left-hand extension G along Uneda embedding and compose this with Uneda embedding, and and we and we want to understand why there is the following isomorphism. But it is so because of the following lemma. Simple lemma says that we have a if we have a functor f from the small category C to the co-complete category E, and we have a functor also K which is fully faithful. To D, then there is a left-hand extension, and also we have the isomorphism that this composite is isomorphic to F. Okay, let's prove this simple lemma. I recall that the left-hand extension is a coent, the following coent, where this operation means copower or tensor product. And then we want to understand what is the composition. Just the following coent. Sorry. Sorry. Okay. And then by neither unit lemma or co-unit lemma, we have that. But at first, we noted that this is just a home set from X to C, and now we can apply the neither unit lemma or co-unit lemma, which states that we have the following isomorphism. Okay, so we proved this lemma, and now we proved the first statement of this of the theorem, and now we can prove the second one, this statement. For doing that, we claim that we suppose that G is continuous. It means that this functor can be moved through the colimit functor. Okay, and then we should prove that the co-unit is invertible. It's quite simple. We can write this composition sorry. We can write this composition what is it? It's the coend just a coend and it is isomorphic to we can apply the usual unit lemma, and then we have the following isomorphism. It is just a PC and tensored by G uneda C, and it maps to the following composition. But by the fact that G is a continuous function. Okay, but this expression is just composition G and P. Okay, and then we see that this is really invertible co-unit, and vice versa. If we have a isomorphism between G and the left kind of extension of the composition G and unit embedding, then we should verify that G can be moved through the co-limit. We can change the order, and it is also quite simple. We consider the diagram in the category of pre-sheaves. Let P denote the some diagram in this category. Then it is isomorphic to the coend tensored by this composition. And now we right. We can we can use the Fubini theorem for coends. Or we know that coend is just a co-limit over the twisted arrow category, and then we can change the order and write first place the colimit functor, and then we can write the coends. And we'll obtain the following expression. And now we can find that this one is just a left can extension of the composition along unit embedding of this presheaf. PG is some presheaf, and this is the same as a colimit of G of the composition. Okay, and the last point. Suppose that we have some continuous functor L from presheafs on C to presheafs on E. And then this functor has a right adjoint. We suppose that it is a continuous functor, and then it has it has a right adjoint given by the coend okay, and I left this as an exercise. You can verify that this is really right adjoint to the to this function. Okay, now I'll give some examples. The first one is as the following. Consider the diagram. From the order category or simplex category and to some co-complete category. And we can try to extend this functor along the unit embedding, and of course it is the case of nerve realization context, and we will obtain the functor L. And what is the functor L? L of X, where X is some simplicial set, is just a coend by definition. And of course, yeah, it is isomorphic to n simplices over X. And this expression, this coend by definition, is the same as a co-equalizer. Okay, and also we know that L of delta n is the same as a delta n because of lemma which is proved which was proved in the proof of the previous theorem. Okay, and also we know that L is a co-limit. It implies that L commutes with the co-limits. And then L has a right joint some R from E to a set. And what is R? We can consider n simplices of the simplicial set R E, and by definition is morphism is a class of is a set of morphism between these simplicial sets, and we now use the fact that L and R are joined, and we have the following isomorphism. And now we use this simple observation, and we have the following isomorphism. Well, thus n simplices of the simplicial set R E are maps in E from delta n to E. Okay, degeneracies and phase maps are defined by means of recomposition in the co-simplicial object delta. Example 2. There is a natural functor from the simplex category to the category of topological spaces, such that delta n is a standard topological simplex. Okay, and we have a junction between these categories. And also we have that the realization of simplicial set X is a coent, and it also can be written as a coequalizer. Okay, the next example. Consider the following diagram. From the simplex category, we have this subdivision functor to the category of simplicial set. And we can embed this, as usual, we can embed this into S set, and we have this left can extension of this functor along unit embedding. And what is d of delta n it is a subdivision of the nth represented simplicial set. For example, if we have the following category, we can consider the following subdivision, and we can take the nerf of this category. Okay, something like this, and here we have a non-degenerate simplices, zero simplices or one simplices, and also two-dimensional simplices is the following ones. Okay, and so, and we can form this functor as D is a left Kahn extension of this functor, and we have an adjunction and there is a right adjoint X functor, and we can iterate this functor, and also we have an obvious natural transformation from SD delta n to delta n. It is a last vertex map. And we have thus we have the following natural transformation, and the corresponding left Kahn extension is we can consider, one can consider the following left Kahn extensions as and natural transformation, corresponding natural transformation, and the colim of the sequence of units for iterated X defines a functor okay. Okay, now I would like to talk about functor tensor product, and after that we will discuss the bar construction. Functor tensor product. Let me define this notion. Suppose that we have two functors, f between the category D and M, and G between D op and some category V. And we suppose that M is simplicial enriched, tensored, and cotensored. M is simplicially enriched, tensored, and cotensored. Then one can define the following tensor product between functors. It is just a coend or co-equalizer. Okay, example, we can think about the R module as a functor from the category with one object with as some category which is enriched over category of abelian groups. We have this functor from the category R op to the enriched category. This is a AB functor, and also.
And in the previous example, this meant that the category M is tensored and cotensored over V.
Yeah.
And it is also okay. I see.
Mm-hmm. And also we can consider the functor B. The first one corresponds to the right R module, and the second corresponds to the left R module. And then we can form the following coends, and it will be just usual tensor products. Where we have a functor, this bifunctor from this category to abelian groups. Okay, the next example states that we can mute the first argument of the tensor product, and then we will obtain just a colimit of the functor f. It is a property of coend, or you can just look at the definition, and then you can find this property. The star means that it's just a constant functor to the terminal object. Okay. And also the next example. We can define the left Kohn extension of f along k as a tensor product. It's just a tautological expression, statement, and for this diagram. Okay. Also, if X is a simplicial set, then the realization, geometric realization of X is a coend or we can write in the following manner. Okay, and the last example. Suppose that X is a bisimplicial set that is a functor from delta op to simplicial set, then the realization of this bisimplicial set is a simplicial set which is just a diagonal of X. Prove this simple proposition. We know that this realization, the coend, and by Ninja-Yoneda lemma, we have that this is just X of kk. That is X, the geometric realization of X is a diagonal. Okay, now we can prove, now we can consider the bar construction, but firstly, I would recall what is the notion of lab deformation of a category, homotopical category, and also what is the notion of lab deformation for functor, for some functor between homotopical categories. Okay. We want to find a convenient lab deformation for the colimit and the limit functors. What is the lab deformation? Let's define this term, left deformation on homotopical category M consists of an endomorphism and the functor Q together with the natural weak equivalence. From the functor Q to the identical functor. And the next definition, lab deformation for a functor between homotopical categories consists of lab deformation for M such that the composition such that F is homotopical, such that F is homotopical on an associated subcategory of cofibrant object as a homotopical on an associated subcategory of cofibrant objects. And there is a theorem if F, the functor between homotopical categories, has a left deformation Q, then the left derived functor of F, if there's just a composition F with the functor Q, is a left derived functor of F. Okay. Our aim is to find such a cofigurant replacement of a diagram, and for doing that, we will give the following definition of bar construction: two-sided bar construction is a simplicial object sorry, not bar construction, but bar complex. Bar complex is a it is a simplicial object for some factor f from d to m and g from the op to simplicial set, where m is a simplicial enriched tensorial and cotensorial. Then one can define the n-simplex of these simplicial objects is just a coproduct over composable arrows from the n to d of these objects. Okay, these notations, this notation means that we have the following sequence of composable arrows in Z. Okay, and degeneracies and SIs and the Is can be defined as from the simplicial structure of a nerve. Okay, and consider as example the first trivial example, not trivial, but not interesting, I suppose, that this bar construction is just the nerve of the category D, when M is a set and V is a set and F and G just constant factors on the terminal object. Okay, and then the bar construction is the realization of this simplicial object. In the setting of previous definition, one can define the bar construction. It is a geometric realization of the simplicial object of bar complex. And it is a tensor product of a delta op these factors. Also, the unique map from delta m to the terminal object induces natural transformation and applying the functor, the following functor. We can obtain the following arrow. From the bar construction, which is a geometric realization of a bar complex, to the tensor product, which is a co-limit of a bar complex. This is an exercise. Okay, the next example is some motivation. Classifying space of group G is just a realization. Is a following bar construction, of course. And why is it interesting for us? Because we have the following theorem, which states that if M is a simplicial model category, then we have the following functor from the category of diagrams from D to M. This is an functor, and we have also two natural transformation, and we want to take their composition. The first one is this one. This one is produced from this observation, and the second one is produced from model structure. This is morphism from. This is just a cofibrant replacement. Okay, and this functor is a left deformation for co-limit functor. Okay, and also we can define cobar construction, and this is a right deformation for limits. I learned this fact. It is obvious. It's dual fact. Okay, what is epsilon q? We have a comparison map. We know that we have map from this map. We have this map from this bar construction to the co-limit of this bar complex, and it is the same that tensor product between press sheaf, representable press sheaf, and functor f. That is it is just a coent but by neither unit lemma, one can find that into the FD, and thus we have the following arrow, the following initial transformation from the bar construction to the functor f. Okay, corollary of this theorem if M is a simplicial model category, and D is any small category, then homotopical colimit over D by definition it is a left-derived functor over usual colimit over D, and it is isomorphic to the following bar construction where we mute the first argument with the constant functor to the terminal object. And in the second argument, we use the cofibrillant replacement functor. This is a post composition with the this one. Okay, and homotopical limit over D is a right derived functor over limit, and it is a co-bar construction with the following functors. Okay, we can derive this corollary from the theorem, and after that we will try to prove. I think I'll give us some sketch of the proof of the main theorem. Proof of corollary. It's so quite simple. We can use the left deformation theorem, and we can write that we know that this functor just a co-limit over this this one. Okay, and then we can rewrite this co-limit in the following manner as a tensor product with a constant functor. And also, why it's true as easy observation. We know that it is a coent, and we have muted coent, but muted coent is just a colimit. Okay, but colimits commute with each other, and coent is a colimit over some category, and thus we have the following isomorphism. We just move this functor into the bar construction. We can do this because of this quotient is a co-limit, and co-limit commutes with the co-coils. Okay, so the derived factor over this co-limit is this bar construction, and we have put this corollary, and now we can prove the following theorem. The previous theorem, prove the main theorem. We want that epsilon. We want to prove that epsilon is a pointwise weak equivalence. As a pointwise weak equivalence. Why it's so? Because as this map was a weak equivalence, and the geometric realization of weak equivalence is also weak equivalence, and hence the composition is also natural weak equivalence, and thus is a left deformation. Left deformation on the category factors from D to M. And what do we want? We should prove that this composition defines a left deformation of a co-limit. To do that, it remains to verify that co-limit preserves weak equivalences between diagrams in full subcategory which contain the image of bar construction. It remains to verify. Okay, and it will follow from the following. It will follow from the next lemma. Some simple lemma. Suppose that we have let deformation on a category simplicial model category, no, not simplicial, just model category M, and a factor between model categories M and N, and if the following conditions are true, that the following, the first one is the composition is homotopical. The second one is the natural transformation from this factor to this one is a natural weak equivalence. Natural weak equivalence, then this pair is a left deformation for F. Prove this lemma. Let phi be a map between the object of the category M, and suppose that Q phi is a weak equivalence, and then we should derive that FQ of phi is also weak equivalence. And then we're done. Why it is true? We know that the composition FQ and Q phi belongs to weak equivalence, weak equivalences, as FQ is homotopic. Thus, form the following diagram. The following diagram. This diagram comes from the neutrality. Here we have this arrow. This we have the arrow of natural transformation, and we know that this is a weak equivalence. This is also weak equivalence, and it is also weak equivalence. And by 2 out of 3 property, we have that this arrow is weak equivalence 2. Three out of 2. So yeah, and thus this arrow is weak equivalence 2. Okay. Thus, according to the previous lemma, it remains to prove that the functor it remains to prove that the functor is homotopical, and that the following composite the following composite is a weak natural transformation. Okay, and for doing this, for proving this, we should discuss slightly reading model structure of the category MD. And let me give the definition. Simplicial object is called greedy cofibrant, if for any inclusion from degenerate and simplices into all n simplices is a pointwise cofibration. And this this inclusion is called the object which consists of these degenerate simplices is called adjunction object. Okay, and there is a following lemma, which states that that diagram is ready cofibrant. When D is a small category, M is a simplicial model category, and if F is pointwise cofibration, pointwise cofibrant. Cofibration, sorry. Okay, the proof. We know that what is the n-simplex of the bar complex is a co-limit over nerve of a nerve category, and we should write this this object, and then nth Lattian object sits inside nth Lattian object sits inside this one at the coproducts indexed by degenerate simplices in this of this one, but we know that cofibrations are closed on the co-limits and push-outs. So we're done. And Also, I will use the following theorem from the reading model structure, from the reading model category theorem. Suppose that M is a simplicial model category. Then we have a realization functor from the simplicial objects in M to M, and this functor is left Wheeling with respect to the reader model structure. In particular, this functor preserves cofibrations, sense cofibrations to cofibrations, and preserves pointwise weak equivalences between simplicial objects. Okay, and then corollary, the functor preserves weak equivalences between pointwise cofibrant objects. So, in particular, the functor. This functor is homotopical. And now we wanna prove that the composite the composite from the previous point. You remember that we have the composition of the of two natural transformations, and we should prove that it is a weak equivalence. And for doing this, consider the diagram from naturality of epsilon. The horizontal map is a epsilon indexed by QB, which is a weak equivalence. As we know that epsilon is a weak equivalence. And also here we have a following map, and here the map Q, which is of course a weak equivalence. And interesting composite is the following one. we should prove that this composition is a weak equivalence, but from the commutativity of this diagram, sufficiently to prove that this composition is a weak equivalence. But we know that the vertical map is a weak equivalence because we know that this map is a sorry. Okay, for doing this, we know that the vertical map is a weak equivalence by means of the Ricci category theory, and it remains to prove that this one is a weak equivalence. This one is a weak equivalence. And for doing that, we should consider the following fat diagram. Now I try to write this diagram. So it's fat diagram. We have that this this diagram we have the following equivalence. We can use the Ninja unit lemma, and we can move this term out of this expression, and we find that it will the following expression. After that, we also use the unit lemma, but now we move the constant factor through the bar construction, and we obtain the following thing. And after that, we use also Ninja unit lemma and move this term into this bar construction. Okay. On the other hand, we can map this one by means of a contraction map epsilon, which is a weak equivalence, into the following guy. It is isomorphic to the following thing, but we have an arrow between this one and this one, and it just this arrow. Okay, after that, we can why we have this in this why we have an isomorphism, because of we have isomorphisms between this tensor product and this constant functor. Okay, and after that, okay, we have the following isomorphisms. We know that the vertical maps is a weak equivalences. Horizontal map is a weak equivalence also, because it is a contraction map. And thus, we have that the bottom arrow is also weak equivalence. By 3 out of 2 properties. 3 out of 2 or 2 out of 3. I don't know. Okay, by this property. Okay, and now we have proved that this arrow is weak equivalence, and then this weak equivalence, and also this weak equivalence, and then the composition is a weak equivalence, and thus this blue arrow is also weak equivalence. Thus we have proved the theorem. And the last point, theorem, let f from the small category D to simplicial model category be a diagram. Simplicially enriched model category, which tensorial, cotensorial, complete, co-complete, and then we have isomorphisms. Where n denotes the nerve of the category. And dually, it's quite simple to see. As exercise, you can check that there is a isomorphism between the bar construction and the nerve of this thing, and then using this exercise, we can find that the coend or tensor products is the same as where I denote by this thing is the representable covariant functor from D to some. Okay, and using this exercise, we can find that we have the isomorphism. And now using the Houdini theorem for coents, we can move this functor into this bar construction. But using the Ninja unit dilemma, one can find that it is isomorphic to this bar construction. And we are done. Okay, I suppose that we have no time, and I would stop at this point, I think.